Hi and welcome to my video series on approximating the area under a curve, which is a lead into integration and the particular application of integration for finding areas under curves. Today we're going to talk about the trapezoidal rule, and this is video 2 of this series. In the math methods curriculum we stop at the trapezoidal rule, so we don't have to go too much further beyond today. So here's the same function we were talking about last time, y equals x squared plus 1. And last time we got an upper rectangle's approximation of 17, a lower rectangle's approximation of 8, and a mid-rectangle's approximation of 11.75. What I'm going to do is just quickly run through how to find the trapezoidal rule approximation, and I'll do it for 3 strips. We did one for 6 strips last time, but I'm going to stick with 3 strips to start with. And we'll talk about that approximation, how close we think it is, whether it's an under or an over estimate, and then I'm going to tell you the actual area. So here we go. 3 strips again, so we do the same setup, and I'll go with purple this time, it's a little bit darker. So 3 strips means we're talking about these 4 points which are the ordinates. They're basically the ends of our strips, and I'm going to draw a vertical line at each of them. Now just to start introducing some of the notation, and there's some variance to the notation here, but typically we denote these as heights. So we have height 1, or actually sorry, typically we call that height 0, height 1, height 2, and height 3. And so 3 strips should end with height 3. And you know, some places you might read, we might have height 1, 2, 3, and 4. In the end, it doesn't really matter. Okay. Eventually, though, it's going to be handy for us to know each of these heights. So 0 squared plus 1 equals 1. 1 squared plus 1 is 2. 2 squared plus 1 is 5. And 3 squared plus 1 is 10. So now I have each of those heights. What I'm going to do is work out the area of these 3 trapeziums. Now you can already see, as compared to the last video, this is going to be a very good approximation. It's a little bit over there, it's a bit over in the middle, and it's a bit over at the front. This is an overestimation because of the curvature of a quadratic in this case. The curvature means that this quadratic is curving upwards like this, rather than curving down like that. If it was curving down, we would have an under approximation. So have a think a bit about that. We can get unders and overs, and it depends on the curvature. You might have functions that have part under and part over, and you get a really accurate value. Anyway, we're going to work out these areas. So the first thing you need to recall is that the area of a trapezium is typically written as a half times height times A plus B, or something else, you know. A plus B over 2H I've seen as well. There's lots of variation. Basically, you just add the A and B, multiply by the height, and divide it by 2 is the end result. In terms of A, B, and height, you've probably seen it like this. Here's a standard trapezium. The height is the vertical height, and A and B are the top and the bottom. And you just add A and B and divide by 2, which creates an average of A and B. And that creates this shape, so we get an average length of A and B, which means this triangle here has been cut off and put here, and this triangle here has been cut off and put here, and you just multiply by the height, and you've got a rectangle, and you get the area. That's how a trapezium works. But transposing this down here, this is your A and B, this is your B, and this is your A, and your height is actually this distance. But we call it W. W for width, because this is the width of each strip. So, and again, you might see it different variants, but we call it the W area. So, our area approximation is going to be a half times height, which is 1, times 1 plus 2. And then the next one is going to be a half times height times 2 plus 5. And the last one is going to be a half times 1 times 5 plus 10. And of course this is equal to a half times 1 plus 2 is a half of 3, so that's 3 over 2, plus a half of 7, so that's 7 over 2, plus a half of 15, so that's 15 over 2, and of course that's equal to 25 over 2, which is equal to 12.5 units squared. And that's good. We know it's an overestimation. It's slightly bigger than our mid-rectangles method from last lesson. Definitely smaller than the upper rectangles, definitely larger than the lower rectangles. So it's a good approximation, 12.5 units squared. And now I'm going to give you the big reveal on what the actual area is. So the actual area can be calculated through integration, and the actual area is 12 units squared. It's hard to believe that that curved area there would provide such an exact answer, but it's true. It's 12 units squared, and most simpler curves will have simple answers. A lot of periodic curves will have answers that involve pi. A lot of curves that are exponential will have answers that involve e, etc., but they're still fairly simple and can be written in the exact form. So there we go. The area is 12 units squared. So there's some generalizations to do with trapezoidal rule, and I'm going to have an appendix lesson. So you'll be able to find it attached to this lesson, if you want to watch it, where I show you where these come from. But what I'm going to do now is I'm just going to summarize the formulas and the calculations, and then I'll show you where this comes from in that appendix episode, which will be quite short and is worth watching, but I'll give you that choice. So generally speaking, if you have any function here, then you can split, to find the area between A and B, you can split it up into n strips. So we've got here our summary there, let n be the number of strips. The area is equal to the width of each strip divided by 2 times by the first height plus the last height, so that's these purple ones, and then 2 of all the center ones added together, and that's these green ones. You have to forgive all the yellow everywhere now. And you can generalize the calculation for the width, and you could do this logically. You can look, A is 2 and B is 8, and we're doing 6 strips, and well, they must be 1 to get from 2 to 8 6 times. Generally, if you just find the difference between B and A and divide by how many strips you need, that will give you W, and that works really nicely. Now, you'll notice here, and I'll just use some light green underline, that H0 and HN are the end heights, that one and that one. So we call them the end heights, and we do 2 times all of these, and they're the middle heights. That gives us our shortened version, which is the area equals width over 2 plus ends plus 2 middles. Or perhaps you might just write the width as this. And of course it was width over 2, so it introduces an additional 2 in there, and so we get b minus a over 2n. That's another option. Or of course you could use the formula sheet one here, which is that. You don't quite know this notation yet, but you will by the time you get to your first assessment on this. But that's basically saying the area between A and B of f of x, or under f of x dx, is equal to a half height times e plus 2m. That's what that's saying. So the e plus 2m is important. I'd much prefer this. It's a little bit more traditional, but e plus 2m works, and so why not use it? A little bit of notation. There's that definition. The integral between a and b of f of x dx means the definite integral between b and a, the area under the curve between b and a, so it looks like that, just so you know. But you will see more of that in about a week. So let's do some examples. Use a trapezoidal rule to calculate the area below y equals a 10th x cubed minus 2x plus 4 between 0 and 5 with 2 strips. And there's the actual area, units squared. So let's do this, and I'll do it in purple. So we're going to start, we want 2 strips. That means that between 0 and 5, so 0 has this height, 5 has this height, we just want to split it up into halves. So we get that bit there. So we have this height, and we have this height, and we have, my apologies, that's at 3. Here, that's at 2.5. That's the center. And so, what do we have? We have that the area is equal to width over 2 times by the ends plus 2 times the middles. Now, let's work out the ends first of all, and we can do this nicely over here. Y is our height, so height naught will be equal to 1/10 of 0 cubed minus 2 times 0 plus 4, which equals 4. Height 1 will equal 1/10 of 5 over 2. 5 over 2 is 2.5 cubed minus 2 times 5 over 2 plus 4, which equals 0.5625. And then height 2 is equal to a half of 5 cubed minus 2 times 5 plus 4, and that's equal to 6.5. So there's our heights at each section, and we just want the area to be width over 2. Our width in this case is 2.5. We could have also got it by doing b minus a, which is 5 minus 0 over the number of strips 2, and that's equal to 2.5. So it's 2.5 over 2 times by the ends, which is 6.5 plus 4 plus 2 times the middles, which is 0.5625. Is that right? Yep. And that's equal to 14.53125. And that seems like a bit of an overestimate, much larger than the actual, but if I draw the trapeziums I've just used on here, well, there they are. And you can see that's a fairly significant overestimate. So let's go on to with 5 strips. Now, there's my 5 strips. I've drawn them on there, roughly. You can see it's still a bit of an overestimate, but again, I can calculate my height. So I get 4. This one here is 1/10 of 1 cubed plus 2 times 1 plus 4. So 1/10 of 1 cubed, which is 0.1, minus 2 plus 4 is 2.1. So this is 2.1. And then 1/10 of 2 cubed is 0.8. And then that's minus 4 plus 4, so that's 0.8. And 1/10 of 3 cubed is 2.7. And then minus 6 is negative, and then plus 4 is 0.7, so that's 0.7. And then 4 cubed, 1/10 of that is 6.4. Minus 8 is negative 1.6 plus 4 is 2.4. And then this one we've already calculated as 6.5. And so the area in this case is equal to width, which is 1 over 2 times by the ends, 4 plus 6.5, and they don't change, plus 2 times the middles, which is 2.1 plus 0.8 plus 0.7 plus 2.4. And that's equal to 11.25 units squared. And hey, we've gone from 2 strips to 5 strips. Not a great deal more working. The numbers are actually a bit easier. And look at our accuracy. It's improved dramatically. Okay, let's do one more, this time with 10 strips. But I'm not going to go through all the calculations. Here, I've had Excel do it for me, and that's pretty easy to do. My F values, I just started with typing 0. Actual fact, what I can do is then just type 0.15 in here, and a little box appears there, and I can just grab it with my mouse, highlight these two, and then grab that little box, drag it down. It will predict what it wants, or what I want it to do. And then my H values, I just put into here. I put in equals. Now let's say this is column A, and that's column, well, that'll be cell 2 because this is 1. I just put in 0.1 times A2 cubed minus 2 times A2 plus 4. And it calculates it for me. And better yet, little box here, I drag that guy down and it will calculate all of them straight up. So it's definitely worth having a play with an Excel. And that might help you with your calculations and practice at home, for example. But then I've just done, I put the formula in here. So that formula will be the width. So I'll probably put 0.5 over 2, or maybe I've even done this cell minus this cell divided by 10 or something like that. And then we multiply that by B2 plus B11 plus 2 times the sum from B3 to B10. Sorry about my writing. And it's come out with this. And that 10.78 is better than 11.25, much better than 14.53, and not too bad at all. If we do 20, 30, 40 strips, 100 strips, which you can do in Excel quite easily, you'll get a really accurate answer really quickly. So there you have it. That's the trapezoidal rule, and also an example of the trapezoidal rule, starting with 2 strips, building up to 10 strips, and how we can use Excel. And this is a reference to our textbook, but also just some understanding of the content that you should be able to use to complete these types of questions. I will say one other thing. The trapezoidal rule comes in handy for one other element, and I'm not going to go into a lot of detail, but here's a task I've done in the past, and there's the working, so you can certainly stop and have a look at it. And basically imagine you had an odd shape on a piece of paper. So it's not a function, which means you can't find the height based on a function. But what you can do is you can use the odd shape and you can determine the heights of each of these with a ruler right in front of you. And if you determine the height and then apply the trapezoidal rule, it's like building a whole bunch of trapeziums. And it gives you a really good estimate of the area of, in this case, that pool or that golf green or whatever it is. It gives you an approximation of the area. In this case, though, I did have to apply scales, and just be careful with that because obviously length scales are fairly predictable. You'll be used to them. Area scales are slightly different. So the only hint I give you is really apply the scale at the start. It makes life a lot easier. All the best.